Today we're going to be talking about running machine learning experiments on inventory management, and we'll talk a little bit more about what that means. Just a high-level agenda for this talk, and also a sneak preview of the talk that comes after this, the DAT 50, which I'll also be giving, and I strongly recommend. We're going to cover a little bit why now, what's changed, and why are we even talking about machine learning and deep learning in these applications. We're going to give a high-level intro, because I understand that in different audiences, people have different backgrounds. Some people are much deeper in terms of their understanding of the different techniques and mechanisms around machine learning, and some people are brand new. So I want to make sure we're all on the same level. And then as we go further, we'll dive deeper and deeper into this session and the following session. And after that, after we're all on the same page, we're going to talk about machine learning specifically on Azure and how you can do the data science process in a way that you can collaborate with others, demonstrate your work, manage, optimize your models and your experimentation, optimize and make sure that you're choosing the right models and get to production as fast as possible. And we're going to show this with a proof of concept, and we're also going to demonstrate kind of what a production style model looks like deployed. And in the next talk, we're going to actually talk about how that model works and the production deployment. So who's ready, or should we get started? All right, I saw one clap, so I'll take that and let's get started. So why now? Well, I think me personally, when I watch this landscape, there's been a big shift in the past 5 years in terms of what's possible. And one of the things that drives this home is this comic from XKCD, which is one of my favorite web comics. If I bring you back just 5 years ago to 2014, we're in the midst of a different type of technological revolution. At that time, we're in the midst of the mobile revolution. And the tagline of this comic is, in computer science, it can be hard to explain the difference between the easy and the virtually impossible. And the premise of the comic, I'm sure some of you guys have read it, but the premise of the comic is somebody has their mobile phone and they want to build an app that tells them whether they're in a national park. And the developer says, that's easy. You just pull up an API, I look up, we're in a national park, there, let's get going. And the person says, that's awesome. Now I want to take a picture of a bird and know that it's a bird. And 5 years ago, and it's hard to imagine this now since we've seen all these amazing demos over the past couple of years around computer vision. But 5 years ago, the response would be, I need 5 years and a research degree, right? Well, if we zoom just 3 years later, this is a project that I worked on in Microsoft in my previous team. Not only could you take a picture and identify that there's a bird in the picture, but you can know what kind of bird is in the picture, where the birds are in the picture, and you could actually track the migration patterns of the birds in real time. And this is real work that we've done at Microsoft utilizing computer vision technologies. And something, when you think about this and you think of that shift from 5 years in a research degree to this type of real-time object detection and these types of models that are becoming more and more commoditized, something has shifted and something has changed. Now, what I'm going to be talking to you today, as you saw around the inventory management, is beyond just birds, cats, and dogs. And typically when you see these demos online, they tend to be very data-driven around these basic classes, detecting cars or detecting cats or birds and dogs, because that's what most of the public data sets are around. But we're going to talk about some real-world applications that, based on some work that we've done with actual customers, and the specific customer and the specific use case that we're dealing with is Tailwind Traders. Now, for some of you who have been following along to this day, you've seen some other amazing applications of Tailwind Traders and how they're using Azure to transform their business. Today, we're going to be talking about a specific scenario. So in this scenario, they've done their inventory management from DAT 10, and they've done the visualizations in the background that you saw in DAT 20, and they've tinkered around with cognitive services that you've seen with DAT 30, and now they have this challenge. Tailwind Traders is a globally distributed company. They have retail trains in almost every country in the world, from the Netherlands all the way to Tel Aviv in Israel or in Silicon Valley and the rest. And they have the following problem. They've done the research and they've seen that if items are not in the right places in the store, people can't find those items, or people are less inclined to buy those items, and that ends up affecting their bottom line. Now, the way they've traditionally dealt with this problem is that they've asked the store manager in every single store, they've emailed them once a month the different stocking arrangements of how everything's supposed to be stocked, and they have somebody go and manually walk across each of the aisles and see if things are out of place and move them around. Now, the challenge is that's inefficient, and a lot of stores, the people who are stocking this are apathetic, and they don't really care about that policy. So they just push the stuff on the shelves, and they don't know where things are, and it's a headache. And to actually validate that each of the stores are compliant when they're globally distributed is also a headache, because it means that they have to hire inspectors or they have to do crowdsource control, and it's a very, very hard process. What they would prefer is they'd prefer, just like we saw with those cats and dogs and birds, they'd prefer to have a computer vision model that can just, based on the security cameras that they already have in the stores, identify what are the items on a shelf, whether they're in the right position, and know whether things are not in the right place. And then they can send out a push report at a specific cadence to specific stores, and they can ask the store manager to go in and ask the person to go make sure that the items are in the right place. And they can even tell the person exactly where in the wrong place those items are so they can put them back in the right place. And you can imagine that the scale of this gets a little bit ridiculous when we look at all the types of items we have. Now, this is a pretty interesting use case. It's based on a real-world code story, and we'll get into that later. And we're going to solve this problem. But before we go deep into this problem, as we're going to go through the rest of this tutorial and also through DAT 50, we should take a step back. Because again, I understand based on traveling to many of these different conferences and working with many different customers in different environments, that people are at different levels or different parts of their journey when it comes to data science and machine learning. So let's take a step back and let's define machine learning from a 101 level and follow me through this journey where we're going to go deep and understand how things work. So in order to understand machine learning, we should take a step back and look at how do we think of traditional programming for solving a problem like this. So traditionally, I might take an image, right, of all those shelves. I have my input, and I'll try to come up with some sort of custom algorithm. Maybe I would look to see whether pixels of certain colors are in a certain index in that image, and if so, I would say that's more likely that it's this item versus another item. And then I would go through each of those steps, and it would give me a valid answer. Is this validly stocked shelf, or is it an invalid stocked shelf? Now, you can imagine that this is a really hard thing to do. What if the lighting conditions are different in a store? What if something's off by a centimeter? What if the scale or the distance of where the camera is different in different stores? All of a sudden, I'm going to get wildly different results. And so traditionally, when we use machine learning algorithms, we're trying to solve these types of problems that it would be very hard for us to come up with a traditional set of instructions to describe our problem and get a standard answer. So we look at, in this case, where we have much more typically stochastic processes or less deterministic steps that we have, we try to look at a large sample of data. We apply our data science process, which right now we'll put in this black box, and we try to derive a model. So that's high level, again, very high level. We're going to go much deeper over the course of this talk and the upcoming talk of how the machine learning process works. Now, what does Azure bring to the table in terms of machine learning? Well, Azure brings 5 steps, in my opinion, that really kind of make this process easier. The first step is we provide many pre-trained models that you can interact with out of the box. For many scenarios, that's good enough. And for those of you who were at Damien's talk earlier, you saw some of the applications of these cognitive services and these custom AI models that you can use and train without having to understand exactly what's going on behind the scenes and integrate them directly into your system. But sometimes those models are not enough for your use case. For this specific use case, those models would be challenging, right? So at the next level, we need to provide tools to be able to develop our own models. Now, when we think of Microsoft as an open company and the open community, there are many different frameworks that we use for machine learning. You may have heard of PyTorch and TensorFlow and Keras, or some of the standard frameworks like scikit-learn, right? And some of the different some of the different types of like computer vision and NLP have their own frameworks and SDKs as well. So what we want is we want to make sure that we have an open platform that allows us to integrate and train for the frameworks that developers use. Additionally, we also partner with Onyx and the Onyx format to make sure that models that are trained across these different languages and frameworks are compatible with one another. At the next layer, we provide the suites for actually processing your data and actually training and managing your experiments and building out your models. So at this layer, you have Databricks, which we talked about in DAT 10. You have what we're going to be focusing on today, which is the Azure Machine Learning Service. And we have also the Azure Machine Learning VMs, which allow you to experiment without, if you don't need that huge batch scale up for doing high-scale, high-performance model computing. And underneath this, we have the compute architecture. And this is also one of the big values of doing machine learning on the cloud, is the fact that you have the ability to scale up on CPU, scale up on GPU that would otherwise be very cost prohibitive, and also for inference, get near real-time inference for many of the state-of-the-art models with custom FPGAs. And when we think about like deployment from this, you have different ways of thinking about deployment, whether that's as a cloud service, as we're going to see today, or whether that's running directly on the edge devices, which we have other demos about. And if you guys are interested in that, I definitely recommend you come talk to me in the Meet the Experts tomorrow. And also being able to do on-premise deployment of our model. So with all of that, that gives us a high-level understanding of what machine learning looks like on Azure. But let's actually drill into how does the pipeline for these different services look. So the first phase of the data science process, that black box that we saw earlier that we're going to dig into, is the data preparation stage. And again, we talked a lot about this in DAT 10. This is how you process your data with Azure Data Warehouse or with Databricks or using some of these other newer technologies like Kusto and Azure Data Explorer. After you've prepared your data and you're ready for actually training the model, this is where we get into the experimental phase. And what we provide here with the Azure Machine Learning Service is direct integrations into your favorite IDEs like Visual Studio Code, Jupyter, but also anything that you guys use to be able to, and we provide the back-end infrastructure to help you manage, build out, and iterate on your models. And that is part of this train test models. And then from there, we also provide the infrastructure for deployment. Today, we're going to be, in this session, we're going to be talking about the preparation and experimentation tools, and we're going to go deeper into what those look like. And in the next session, we're going to go a lot more technically, in a lot more technical depth, and we're going to focus on the deployment story. So let me take a step back and kind of show you what this looks like. Okay, so here we have Visual Studio Code running. And within Visual Studio Code, I have two projects. So typically, when I'm working with the Azure Machine Learning Service, I do two things at this level. One is I have my model code, which I put in a train file, train.py file, and I have a score.py file, which later I need when I have my model for evaluation. Right now, we'll focus on the train file, and essentially, we'll dive deeper into this code and what it's doing in a little bit. I'm going to take a step back now, but the general idea is here, I can code in using any framework. Here, we're using TensorFlow. I can use PyTorch, Keras, whatever I need, as long as it's running on my system. I can run within a Docker environment, whatever I need for development. And through this, I can integrate directly with the Azure Machine Learning Service. So let's go back to the presentation. We'll talk about the next phase of this pipeline. All right, perfect. So the next phase of this is, as a data scientist, and where production data science typically breaks down when you're scaling out, is working with others. Typically, when I'm building a model, I'm not working alone, right? It's one thing, we used to have an old joke at Microsoft called, "It works on my machine," right? And there was once a story of a person who always said that, and they bought him this cake. The challenge is, in the real world, you don't work alone, and you need to be able to collaborate with others, and you need to know that the code and the model that you're training, that others can access, that others can see what you have done, that others can integrate with the same data sets that you're working with, and that they can build and integrate with that. So the way we do this is through the Azure Workspace. And the workspace is made up of the following 6 components. The first aspect is compute. And this is how I manage my group resources and the group compute for the different types of models I'm trying to build. Maybe I'm trying to use scikit-learn and I don't need a heavy GPU cluster to train that kind of model, right? Or maybe I'm doing something where I'm training on ImageNet or very, very large data sets, and I need much higher scalable compute. So I can manage this as a team in my workspace. Additionally, on top of the compute, we have the experiments that I showed you earlier, where I can run my own code, I can deploy my own code, and all of that can be managed in experiments so that I can see what I've tried versus what other people have tried. And also, if you've ever, as a data scientist, worked on something and thought about what was it that I did 5 experiments ago, I have a direct log of all the experiments I've run, all the code that's been published, and so I can actually see and manage that. The other aspect is data, right? Well, it's one thing when we're dealing with smaller data sets, which you'll see in this demo, but when we're dealing with large data sets, we can't necessarily just move data around from machine to machine. And the ability to store data and link data to our experiments in a centralized location that can be used by my entire team is a big value of the Azure Machine Learning service. After that, we have to think about the model management of how do we do iteration of models? How do we do deployments of models? How do if I have a model, how do I remove a model or go back in time and retrieve an old model if I find an issue with an existing model? And so model management is something that's directly integrated into the Azure Team Workspace. One step on top of the model are 2 things. One is images and deployment. Images is, it's great that I have my model file, but I still need all the dependencies and all the background to actually run and execute this model. So I do that I can manage that within containers. I can actually deploy that as services. So behind the scenes, what's really nice about each of these services is they run on the other existing Azure infrastructure that I already have. So for instance, things that you know, like Azure Storage, Azure Container Registry, like ACI and AKS, things that I already know as part of my DevOps work style, this service integrates directly with them. Key Vault for making sure and managing access to my APIs and access to evaluating on my models when I've deployed them. And Application Insights, which we'll see a little bit later in terms of how you actually manage the types of requests that come in. So that's all great, but you guys are probably wondering, what does this look like? So I'm going to give one more slide, and we'll go directly into demos. In this one slide, it will show exactly how these different components within my team workspace that I need for scaling out experimentations and ML all link together. So I start with my computer in Visual Studio Code, exactly like what you saw before. I define my train script, I define my environment, I define my score model, and I send that up to build experiment. With my experiment creates a Docker image with all the dependencies that I need and links it to the compute targets that I've specified that I can auto-scale, so I don't, based on my model needs. Additionally, it will go to my data store and will link to the data and the information that I need so that I can have everything without having to store that I don't have to worry about how I store and manage the data sets that I've spent all this time creating and building or generating earlier within services like Azure Databricks and the like. Then it will launch the script in the Docker image on top of the compute target that I've defined, the train script, and it will link the stream output, the logs, the metrics, directly back to my experiment, which can stream in real time to my computer and my client, so I can manage it as if I'm on the device. So this is all great in terms of slides, but I think it's worthwhile to actually see what this all looks together. So I'm going to give you a very high-level look first at the portal of what this workspace looks like, and then we're going to go to a real-world toy example of how these things work, and I'll explain why in just a second. So if I go here, can you guys all see this? Let me make it a little bit bigger. This is the Azure portal, and this is the Azure Machine Learning workspace. From here, I can dive in to my workspace, and I can see directly the experiments that I've built. So one of them is ULO v3. That's the object detection model that I've custom trained for the task that we talked about with Tailwind Traders. And the other one is sample MNIST, which we're going to dive into a little bit, exactly how that works behind the scenes. And I can see information directly in the dashboard about the runs, about how much time it took about the jobs that I have actively going, which have finished, how long they took, their performance in terms of the different durations and runs. I can modify the pipelines that are needed in order to link data and everything that I need in terms of my DevOps workflow into this, into my applications and for my machine learning models. And I can also manage my compute resources for both deployment and for training. I can manage the previous models that I've trained, and I can go directly from them to create images which I can later deploy either on the cloud or push on the edge for on-the-edge deployment. And all of this within the portal. So again, all of this is great. Let's actually take a look at how this runs behind the scenes. So to do this, when I'm explaining a new service, like before we talked about Tailwind Traders and that object detection model, and I promise in DAT 50, we're going to go deep into that model. But when I'm explaining how a new service works and all the components of a new service, what I like to do is I like to take a step back. I like to think of what's the most simple model that I can build that demonstrates how everything works so people don't get confused by the model or the use cases of what I'm building, and I can focus directly on the actual pipeline and tools for our training on. So in the field of computer vision, the standard toy model or toy data set for this is MNIST. How many people here are familiar with MNIST? Can I get a couple hands? All right. So that's interesting. I would say about half the audience is familiar with MNIST. That's good. For the rest of you, MNIST is a data set of 60,000 images, each 28 by 28 pixels. They're all grayscale, so there's no color. It takes out a lot of the complexity. They're very small, and they all link to an individual number. So when you look at this, you see that we have a bunch of different handwritten digits. We have labels that are linked to the actual number, and our task is we want to be able to see when we have a new digit to be able to classify it. Behind the scenes, when you drill into this, the actual image, 28 by 28, they look exactly like this. Again, no color channels, no anything like that. You have essentially a matrix where 0 if it's white, and then the different intensities. So if I'm looking at this and you're looking at this, you can see that this is a 5, but the computer would have to learn that, and we have to train that, and we'll walk deeper into how that works in the next session. But right now, we're going to take this data set, and we're going to show how you would train a model using Azure Machine Learning. So I'm going to walk back. I'm going to go to Visual Studio Code. From Visual Studio Code, I'm going to run a Jupyter Notebook. And within this Jupyter Notebook, I have my Azure ML workspace. Can everyone see this? Let me know if you guys want me to zoom in. Does anyone want me to zoom in, or can you guys read that in the back? Can you read it? All right, perfect. That's great. So the first thing that we have here is the imports that we do, right? And what's really nice about all the demos and all the samples that we're talking about today is that everything is open sourced. So everything that you see here today is something that you can later clone and experiment and play with yourself, and we'll put links at the end of the session. And so the first thing that I want to do is I want to create or link to my Azure Workspace. So what I do is I need 3 things: my subscription ID, my resource group, and my workspace name. In this case, because those are things that I wouldn't necessarily want to share, I can also save them to a config file that's not publicly visible, and I can load directly the config file. So now that I've done that, I have my workspace. From there, we want to create the compute that we're going to need to run this experiment, right? So the way I do that is I define a compute target and a cluster name. And what this code is doing here is it's saying, does the compute target already exist because I've already created? If not, it will provision a new compute service. And what's really nice about this is I can define what is the VM size that I need for my experiment. So for instance, if I have a big deep learning model, like the one that I would need like I needed for Tailwind Traders, I can define the N series with stronger GPUs on them. And I can also define there might be different phases where it needs more GPU memory or more processing power than other phases of the training cycle. So I can define min nodes and max nodes, and all the auto scale of training and dealing with the service is managed by itself. The other thing that's really nice about this is that in the past we had this service called Azure Batch AI. That's been now rolled into this one call. So I can actually define low priority instances within this function, which allows me to cut the costs for training models tremendously. So after that, I will create the compute target. So let's run this cell. And then let's look at what it looks like to actually run an experiment. So again, very, very simple. Essentially, I define a new experiment. I give it my workspace, and I give it an experiment name, and I define the source directory. Now, you see that there's like this little dot here in the source directory. You're probably wondering, where is that? Well, there's a very simple answer for that. When I went into Visual Studio Code, everything here, all the code, all the stuff that I'm dealing with as an individual is on my local machine. But it will get bundled up and submitted as an experiment. That enables me as an individual developer to tinker and work and make sure that certain things work locally. And when I need to submit it as a cloud job through an experiment. But it also enables others to see exactly what I'm doing as I'm training. So it enables that collaboration we talked about earlier. So right now, we're going to run the basic model for creating a MNIST classifier. And you can see kind of how this works. So we have the different logs that show the different batches and actually what the training process looks like. Again, for those of you who understand what that is, that's great. For those of you who would like to learn a little bit more, I strongly recommend the next session of DAT 50, where we're going to do a deep dive into how all the computer vision works behind the scenes. And I can see all these different stats in terms of the batch size, the learning rate that was defined, the amount of epochs I told it to run. An epoch is, if I go through all my data once, that's considered an epoch. And I can see in real time, as the model's training, I can see how the accuracy is changing over each of the periods of the epochs. And I can also monitor the cost from a GPU perspective and compute perspective to see how that's going up and down as the service runs. And I can also look at my loss and manage that as well. So, okay. That's great. Now let's talk about the next things that the service provides. So all of that's great. Essentially what we've seen up until this point, to do a quick recap, is we've seen the power of the Azure Machine Learning service to take models that I can get running locally, to allow me to scale them using the cloud, to allow me to collaborate with them using the cloud, to allow me to monitor the training process using the cloud, to do that in a way that's cost-effective using low priority instances and with auto scaling. But there are additional things that make this process a little bit easier. So typically when we're building machine learning models, there are a lot of things that are called hyperparameters. What's a hyperparameter? Well, hyperparameter are the different features or the different values that go in for the configuration of different kinds of models. So for example, like where the data set is would be a parameter, but for a specific model, the batch size or the learning rate would be considered a hyperparameter. It's something that's not hard-coded. I tune it. So what's a batch size? Well, typically when I'm training like neural computer vision models, right? If I set the batch size to 1, that's the equivalent of every time I run through the model, I go one image at a time, I calculate the loss, and we'll talk about that again more, what that means in the next talk. And then I would update the weights of my model. If I have a larger batch size, it means instead of doing that on each image, I take 3 images or 5 images. In this case, defaults to 100 images. I do a feed-forward step to understand all the losses for each of those individual images. I average that, and I propagate the average of the loss back. Now, what's challenging about these types of parameters is, depending on these configurations, I don't necessarily know in advance, they can affect the performance of the model and my results. If I'm an individual and I'm manually doing this optimization, it means that if I want to find the optimal values, I need to run multiple experiments. And locally, I might not have the compute to distributively scale each of the different hyperparameters to get the right results. So one of the things that the Azure Machine Learning Service provides is it provides the ability to do auto hyperoptimization and configure those parameters for me and run multiple copies of my experiments with different range sets of hyperparameters to find the ideal value. So let's look at a little bit what that looks like. So in this case, I have my data, and I'm going to define the experiment here. We have we're going to use a random sampling or random search. And the way I do this is we use 2 things. We use what's called the bandit policy, which provides early termination. So it says essentially, for specific cases, if we're not seeing improvement of a model over a certain period of time, kill that model and instead try with different values to see whether we can get better results. And I also have this hyperdrive run configuration. And in this, I pass the model, the estimator I'm trying to train. I pass the metric, and I define the hyperparameters that I want to examine over a given uniform distribution or over a given set of choices. So for my learning rate, I'll do a log uniform distribution. And for my batches, I'll give it a choice of a batch size of 16, 32, 64, 128, 512, right? So let's look at what a run of this looks like. We're going to quickly run this. And give me 1 second. And what we can see is over here, and this is a model that I'd run before just to save time, but we can see all the different models with different configurations. We can see which one was the best given the metric of accuracy that we provided. We can see the durations and when the early stopping for different kind of models were. And we can configure all that. And I can actually visualize in different visualizations what's the difference, what's the effects of these different hyperparameters on my model. And there's also some really cool like visualizations. For instance, I can do something like a 3D scatter chart. And I can see all this plotting and visualization, which I get for free using the Azure Machine Learning Service. So that's great. And again, it's a powerful thing. If you've ever had to manually do this, doing TensorBoard or writing your own visualization or writing individually scripts for managing many concurrent jobs, you can imagine it's not the most fun thing to do. And this allows you to do it seamlessly with a couple lines in an API. The last really cool feature that I want to show you today is the concept of AutoML. And so what AutoML enables us to do is not all of us have an on-staff data scientist, or maybe we have a couple ideas that we want to experiment with the data that we processed and created before. And we want to take that data, and we want to try to generate a model, right? We want to have a baseline to understand what the value of that baseline is before we bring in the data scientist, before we invest deeply in terms of optimizing what that model is. So what AutoML allows me to do is it allows me to provide my data, define the goals or the metrics for my data, and it will test many different out-of-the-box algorithms in parallel with different stopping mechanisms to make sure that if a model doesn't seem to be converging, it will auto-terminate it, and it will try to determine based on these out-of-the-box algorithms which one provides the best baseline results. And where this is very powerful is this is not like the type of thing that will replace your production model. But what it will do is in many cases, and a lot of the customers or use cases that I've worked with, before people invest heavily in optimizing and developing a model, they first want to see whether they have market fit. And one of the best ways to do that is to have a baseline model, and the easiest, best baseline model that you can have, and you first deploy that, and you see what are the improvements of that over your current business use case, and you see what are the effects of the engagement or the optimization of that model, and then you can see and you can make a better informed business decision based on the performance of that baseline, whether you should even invest in this kind of model or this kind of use case. And so what the AutoML service allows me to do is it allows me very quickly to go from the data that we created and generated earlier from DAT10 to getting a very quick baseline that I can use to benchmark and to understand whether a use case is worth diving deeper into. So let me show you a quick demo of how that works. So here we have our AutoML settings. These are the things I was talking about. I can define what are the constraints of the different models that we want to try, how many iterations, should we do different folds of cross-validation on our data, what's the metric that we should optimize for, in this case, accuracy under the curve. We can talk about concurrent iterations, how many models I should train in parallel, which I can increase depending on how much I increase my dedicated compute resources. And we can define our tasks. So in this case, we're dealing with MNIST, classification task. I have an image of a number, and I want to classify what number it is. And from there, that's pretty much all we have to do. We define our experiment, and we run the experiment. So I ran one of these earlier, and I'll show you kind of what the results or what this looks like when we run this model. So essentially, I can see here different types of models, which ones failed because they're not a right fit, which ones were early stopped. I can do ensembling of some of the different out-of-the-box traditional models, and I can see very, very quickly which one gives me the best results. And I can also, just like before, we can see for each model how the different, just like we did with our hyperparameter optimization, we can see how the different configuration settings of the model affect performance. So we can also, there's some other really cool things that we can look at. So for instance, in this case, we optimized for area under the curve, but we can also say we might care about other metrics as well. So we might want to see the different types of metrics and benchmarks for evaluating our model, and we can look at all of these out of the box. And for a specific model, we can actually dive into and try to understand a little bit more about that model and what's going on behind the scenes there. So we can see the charts and the metrics for the specific run, all the accuracies and metrics for the specific model. And I have the different model names, so I can later dig into them and try to understand better what these models do and whether it's a good starting point for diving deeper. So the one last thing I want to do is I'm going to show you right now, as we sum up, we're going to end a little bit earlier, but I think that's good because it will give you some time for the next session as well, is I want to tie this back to Tailwind Traders. So right now we've talked very high level about MNIST, about how the entire pipeline and process for doing machine learning experimentation and for production is done in Azure. I want to show you kind of a demo of what this looks like for the model that we built for Tailwind Traders. So here, let me zoom in for you. Can you see it in the back? Perfect. OK. So essentially what we're going to do here is we're going to define the code for visualizing the model. I have my endpoint of the model that I trained earlier that we'll be deep diving through in the next session. And I have this image that we're going to pass in with a bunch of items on a shelf of cups, of bowls. And what I'm going to do is I'm going to pass this image to the service. I get a response. The response is back in JSON, so I can run that response, and we can see where each of the predictions are and their confidence. In my draw function, I can even filter on confidence. So if I'm not confident about a given object, I can filter it out. And very, very quickly with one line of code, and you can see that I've run this before, but I'll run it again. We can see the object detection model running in real time on the cloud. So really, I'm going to tie this all up right now. Let me see if you can finish this up. So I just want to do a high-level review of what we talked about. So in this session, we talked a lot about the different Azure AI tools, specifically Azure ML, and what the Azure ML service brings to the table for people from data scientists to DevOps experts. We trained an MNIST model with the Azure ML services, and we saw how we can scalably hyper-optimize the parameters. We showed, additionally, how we can use AutoML to build out different models from our data without actually having to supply a model architecture. And we demonstrated the real-world model that we'll be diving deeper into in the next session. Again, I know I've been giving a lot of plugs. I strongly recommend the next session. If you want to learn more about this, I'll leave this up for a second if you guys want to take a picture. We have some really interesting docs around everything I showed you today. We have our learning resources to diving deeper with Azure ML Service, and some tutorials, resources, and blog posts that I've written as well if you're interested in that. And all the session content and code is open source and available online for diving deeper into it. And I want to thank you guys for coming. And if you have any questions for me, I'll be around tomorrow at the Meet the Experts. And I look forward to seeing you guys in the next session of DAT 50. Thank you.